Please? You can hear me? Yeah. Okay. So, okay. So let's continue the discussion still on single species. Actually, I wanted to talk about this yesterday, but we ended up with a long discussion, which was actually nice. So we have seen the dynamics of a single species in continuous time. Okay, that's if you come from biology, maybe you say, what is continuous time? It's just the time flowing norm as we know it. Okay, it mathematically means that when I talk about n of t as a function of time, this t is continuous. It's a real value from 0 or to infinity or to some value. Okay, so that's you'd say, okay, and we fill the time flowing continuously, so therefore that was okay. Now, there are problems in which the species you are studying lives in continuous time, but sometimes you have situations where there are generations which do not overlap. Okay? So this is typically dynamics that most of the time is from year to year. So that there are species that you only observe in a certain part of the year. Okay? Let's say that's pretty much common with insects. Right? So then they disappear. Then you would say, okay, how can they reappear from nothing? Okay? Now, they put eggs, and sometimes these eggs have biological mechanisms that when some stimulus comes, maybe temperature or just sunlight, they will give birth to, they eclode, they give birth to the next generation, but the first generation has already gone. Okay? So it's non-overlapping. Okay? Well, you can also think maybe the first generation is not completely gone, but maybe they overlap a little bit. But you see, one way of studying this is instead of looking at this dynamics in the continuous time, which you can always do because time flows continuously for us, and it's maybe better to model the system by generations. So I will say, for instance, if there's a certain generation time, okay? So we have the first generation, then has a certain size, population size. Then you have the second generation, and the third, the fourth, and so on. So time can be used instead of continuous, counting generations. So you count generations, okay? And this will be appropriate for this non-overlapping systems. Sometimes this can also be used as approximation for species that have overlapping generations, but your observation can be done only on a certain moments of time. So it's non-observable between things. Okay. So we want now to formulate this in a mathematical sense, and we will start by rewriting the Malthus exponential growth in discrete time. So okay, this is jargon from mathematics. Discrete is something that's not continuous. It's from 1, 2, 3, 4, from number to number. It's not continuous. Okay, so this means discrete time. Okay, so discrete time, generalization of Malthus law, and then we want to discuss the ways to express population regulation from in the same way we did with the logistic equations and in the generalization of logistic equation that we have discussed yesterday. So we want to do the same thing we have done, but in discrete time, and we want to see if things will turn out to be very different or not. Okay? Well, so the most obvious thing is saying that so discrete time, let me ask you, is my writing, my letters, large enough for the people in the... So discrete time, so you will have a certain time, which is now our time scale, right? Which is the generation time, okay? Okay. Is it clear what that generation time should be? I mean, I have one generation, and then there's after some time I have the second one. This interval is the generation time. Okay. So then somehow you will say, I have now time is not anymore in principle continuous, but you would say that your generation at time t plus so I want to calculate the I know n of time t. Okay, let's say maybe t is just 0. Okay, at the initial moment. I know it at the time t, and I want to calculate the next generation. The next generation will be t plus capital T. Okay. So if I go for Malthusian growth, okay, then I would say that this is just proportional, and I will use an R, to n of t. Okay. Now, some observations. First one, this is, people use this R, but this is not the same R that we had before. It has some relation to it, clearly, because this is something that relates the population at time t to the next generation, but this does not have any dimension. It's a dimensionless thing. And remember that what we had before, R gave us a time scale, because the dimensions of R were 1 over time. Therefore, 1 over R is a time scale. This R has no dimensions. Okay? The time scale is already given from the beginning by the generation time. Okay? So now, this doesn't look well. This is there. Okay? But you want to count first generation, second generation, third generation, and so on. What do? I can define a new time variable, which I will use this way, and say the new variable is time over generation time. Okay? I'm taken.
Can you say it again?
I will do a mathematical trick. Okay? The mathematical trick is I want to introduce some time that has no dimensions, because the capital T is the generation time, so it's an hour, seconds, years, whatever. Okay, and therefore, this T here is also the time in dimensions, hours, and so on. But if I divide my time variables to the generation time, which is just rescaling things, okay, I will have a new time variable which has no dimensions, because you have, say, hours divided by hours. So this is just a new time variable which refers the time to the generation time. So it will be a counting time variable that counts generations. Okay? And if I do this, then I will have here n now of t new variable plus 1, because this guy will also be now divided by capital T, and this will give me r of n of t. Okay? So now everything is as we would like. We have here generation in generation, say, 1, then this calculates generation 2. Time, once I have 2, I can put it here again and calculate generation 3, and so on, and so on. Now, it's the same because it has no dimensions. If it had dimensions, this is the different way of writing R. Yeah, one was more script. It's the same, yeah. So now, I just want to be sure that people that do not have a strong mathematical basis are following, because this will happen all the time. We will use, when we will discuss Monday, two species competing, we will use this idea that we can transform our variables that actually are related to the species and the times and so on to something which has no dimension. Okay? And then do all the calculations with no dimension, and if we want to go back to what a physicist would call physical variables, and maybe we could call it biological variables, you have just to rescale back. So this is just multiplying variables by constants. Okay? So I just multiplied, in this case I divided my time through some reference time. Okay?
So just to confirm, so you have a generation time, a specific generation time for a species, like 4 hours or something, and you want to use it as a unit of measure for it.
Exactly.
And then you divide it per generation time, just to, okay.
Yeah, and T now goes, the new time variable now counts 1, 2, 3, 4, 5.
Okay. So now you have a measure of frequency which is dimensionless.
Yes.
It is? Okay. Okay.
Everything is dimensionless. Now, just pay attention. I will do something that physicists do all the time. It's saying, I don't want to go around with this notation, with this guy here. So I will just drop this and say now that we have this, but remembering that this is the non-dimensional. It's just for notational simplicity. Okay.
Are you here?
Yeah.
This is like a recruitment rate.
No, this what, the R or?
Is n type plus 1.
No, n is just the population size, right?
In one generation time.
Yes, you think that we will look at the size of that generation, okay? And so you say I have something which is annual, okay? Say the generation is 1 year. This is very common for plants, for instance. Okay, so they have the generation. This generation has, maybe it's flowers or something, flourishes in May, and then this is the population size in May, from the year 1, and then the next one will be the population size of the same species in the next year, and the other year, and so on. That's it. That's what I mean. It's the size of the population. Yeah, I mean, you could say, but it's exactly at which point of time. This is not the way to interpret this. It's the size of this population, okay? Yeah, because obviously there's no such thing that really is all the generation at the same appears from instantaneously, and then okay, there's always some curve and so on. So there's approximations, but the idea is this: I have generations. Generations have size in the sense total number of individuals present in that generations. And I want to calculate generation by generation the population dynamics, okay? So say I know the population at time. Okay, so just one thing. This is a notation that is, I mean, this is common, and usually I have used this, yes? Okay? This is common, I mean, you can interpret the things as you like. But the common way is that this is for continuous time, because it's the function of the time. Okay? So you could obviously also write what I wrote here in this way, but it is common usage to take this subscripts saying that this is a function of time, okay? But it's in discrete time, okay? So it's a convention only. Okay. Okay. So you say, I know at time 0, okay? Then this implies that at time 1, I have r times n times 0. Now I want the time, I know n1, okay? So this implies that n times 2 is r times n1, which is r squared and 0. Right? Now I know n2, which implies that n3 is r times n2, which is equal to r squared n1 cubic and 0. Okay? No? Not okay. The people say no, they're not okay. So I have my population at time 0. Okay? The time 0 is the first generation. You have always, either with differential equations or with discrete time. Sometimes these are called difference equations. It's also just a jargon. You have always to state your initial state. I begin with something. Otherwise, I don't have solutions. I mean, you cannot have something when you don't have any initial conditions, okay? So I have initial conditions. So this is n0. I plug this into this equation. I put a 0 here, and therefore I have a 1 here, okay? So n1 is r n0, okay? Now, I want to know n2. In order to know n2, I have to have n1 here, but I already know n1. Okay, so n2 will be r times. It's just the formula, but I already know this guy from here, which gives me r squared and 0. And then I continue with the same iterative method. I want to know n3. In order to know n3, I have to know n2, but I already calculated n2 in the previous step. So n2, n3 will be r times n2, which is just the formula, okay? Which gives you n2, but I already know n2, which is okay, r squared and 0, which gives you a cubic, okay? So just go on iterating. And here you already see that if I go on with this thing, I can get this at any time, okay? This at any time, because it will be just the power. N3 is r to the cubic. Okay? And N4 will give you R to the 4th power, blah, 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 blah. So this is give you at an arbitrary time will be just the R power to T and 0. Okay? Nice. Okay. So that's what we call the Malthus law in discrete time. Now, let's see what it implies. So this guy here, which is the R, okay, which is kind of just some multiplicative factor from one generation to the next one, and we are considering, obviously, that from one generation to the next one you have some factor, which is the R, and the same factor for for all generations. It's always the same. Okay? So this is a mimics the idea that you have a constant birth and death rates. Okay. Yeah.
So in the Malthus continuous model, the R was the rate of evolution, right?
Yes.
So in this case, it's not adimensional, so it's like a proportion of evolution.
It's a proportion, yeah.
Okay.
It is the well, if you remember your high school times, you probably had what people call a geometric progression, and there's a step of the this is exactly a geometrical I have geometrical progression is something you have to give the rate, okay? And, I mean the proportion from step to step. So you start with, say, the proportion, say, is 2. So a geometric progression would starting with, say, 5 would give you 5, then you get 10, then you get 20, then you get 40, and so on. It's exactly the same thing, right? And this is the general term of a geometric progression. Okay, that's it. Exactly the same. Okay? So you can then also, I mean, it is possible, but to show that if you then go back to the variables with dimensions, and I take this guy going to 0, this will approach an exponential. Okay? Just believe me, I don't want to make this calculation. Okay? So, what does it say here? Now, if R is smaller than 1, decrease. And population, let me write it mathematically, but it just means that for time going to infinity, the limit of n of t is equal to 0. Okay? After many steps, many generations, it decays. Okay? And well, if R it's bigger than 1, then you have increase. Yes, it can only increase, but you have a factor, and you have the power of this. From time to time, you will have more and more. Okay, you see, say R is in this example 2, then here you will have 4. Okay, and then here you get 8. Yes, okay, so it's by powers, and it will go without limitation. Okay? If you want to write it with a little bit of mathematical jargon, I don't know if biologists have seen this. Sometimes this means the limit. I won't define mathematical limit and all, but it's just the limit when the time is very large of this function is 0, and in this case it is infinity. Okay? So Malthus gives you infinities. Okay, we expected this. Okay. Okay. So there's no much more to say about this because we discussed already Malthus law and exponential growth and all these things, and I won't do it again because it's essentially the same thing, just by doing step by step instead of continuous time. Okay, so the biology, which I remember, I always say that you have on one side of your equation you have the time variation of something, and the other side you have to translate the biology that your hypothesis about the biological process that create the change of the population size. And well, in this case, it's also just that R is a constant, which means that from generation to generation, I just have a multiplication, and that's it. Okay. Okay. So it's the general setup is this one, but now we will go back to our two previous classes and say, okay, now we want to discuss the populations that do not grow to infinity, population regulation. In the same way, we have discussed the logistic equation or the Ali effect or whatever. Okay, so then in this case, I cannot go on with this constant R. Okay, because otherwise So I need to have some regulation of the population, and we want to do what the biological ecological jargon says. It's density dependence. People actually, this is a number dependence because we are counting things. Density is something which is usually refers to space, but okay, the jargon is density dependence. Okay, yeah. So density dependence. We want to go to density dependence. Well, and here now we will have some fun, okay? Because this one is not so nice, okay? So I will have still the same thing. The population, and I know the population at generation t. I want to know the population at generation t plus 1. But in principle, this is any function of this. Could be any function, okay? Now, could be any function in the sense, mathematical sense. Obviously, we want to look for mathematical, for functions that express some biological facts. So, the first thing is, okay, we want density dependence. We want that if you have a larger population, the growth rate should be smaller and smaller. This is density. That means that as you have more and more individuals, from one generation to the next generation, you have a smaller and smaller rate of reproduction because of competition and so on. We also discussed this lengthily. Very good. So we will do the first thing that somebody would think about. Well, say, okay, we use a logistic, we want to use a logistic again. And then you'd say that, oh, well, I go for logistic case, which I would say is just putting the same functions we had before, like R, n of t, 1 minus n of t over k. Okay? Now, rescaling. Okay. I don't want this key. What can I do? I can give a new variable, which is the population size, referred to the carrying capacity, which normally would be, if most of the time, the fraction of the carrying capacity that the population represents. So I want to call it this guy here n of t over k, some n of t this way, okay? Anything here, and then this becomes, with this k disappears, and if I put it here and here, that will also disappear, and with this I will go to where now I dropped my special symbols here, and I'm back with the notation, which is the simple notation. So this is my logistic model. By doing the first thing that comes to your mind, we modified Malthus by putting the logistic term, and we had the logistic differential equation. And why not do it the same thing with the discrete time, okay? Okay, well, now we want to know the dynamics, how this population will evolve in time. Well, you should do the same thing, okay? You have some n0, then you should have say, n0 implies that n1 is r times n1, 1 minus n1, 0. Okay? We start with a population at time 0. At the generation 1, we have this. Then I want to calculate, I know n1, I can calculate n2, which is r times n1, 1 minus n1. Okay? And n1 I know from here. I got r squared and 0 here. 1 minus n0. 1 minus r0 r and 0, 1 minus n0 here, and so on. Yeah. Now this doesn't look very well, okay? But it's exactly the same thing I did here. I just take my population at time 0, calculate at time 1. In order to calculate at time 2, I use the same expression, so time 2 depends on time 1, but time 1 has been calculated, and I can substitute here and go on, okay? So
at this n with this line up, why did you wrote like at this?
I dropped the symbol here. Okay, this equation would be with this, okay?
But why the k disappeared? I don't.
Why the k
disappeared?
Okay, I can do it. Okay, so I will have therefore n with the superscript or whatever is equal to this. Okay, therefore, in order to go from this to this one, okay, that's the question, yeah?
Yes. Yes.
Yeah. I will have to write n of t. Okay, so this is n of t is equal to this new n, okay, times k, okay, from here.
Yes.
Yes?
Yes.
So n of t plus 1 here will be n t plus 1 times k. Yes? And this has to be equal to this one. Okay? Yes. So this is r times n of t, but n of t is n superscript times k, 1 minus n over k, but n over k is just this guy. Yes? Because the cancel of them. And here, k cancels with k. And what at the end, you get this. This. Okay?
So this is a proportion of
Yes, a proportion. It's the fraction of the
the fraction.
carrying capacity. I mean, say carrying capacity is 200, and my n is
100.
100. Then this new variable here is 0.5.
Okay.
It's the fraction of the carrying. I mean, it's the proportion of the carrying capacity. So you are counting your individuals in using the units of the carrying capacity. Okay.
Okay, but why at this n0? So this n0 is also a proportion of carrying capacity, or no?
Here, yeah, okay. So what I do then is, I don't want to carry out all the time the symbol here. Okay. So I just drop it.
But this number needs to be a proportion.
Yeah,
Of
this
carrying
is now a
capacity.
proportion. Okay.
But at the other, like
Here,
n0,
yes, this is a proportion.
this is a proportion.
Everything now is being referred to the carrying capacity.
Okay.
Instead of counting individuals one by one, I take the number of individuals and I see what proportion of the carrying capacity I have. Okay? So usually you'd say, okay, this will probably be something between 0 and 1. Okay? But you can have overshooting. I mean, I can have overshooting. You can have higher values at the carrying capacity, then you probably go back. So it's not that between 0 and 1, but because of overshooting. But otherwise, it's most of the time, and the simple dynamics without overshooting between 0 and 1. Okay?
Okay, thank you.
Okay. So all of these are proportions. Okay? Now, okay. So everything has no dimension, and n is a proportion, and the time is counted by generations, and therefore there's no dimensions at all in this problem, and this equation has only one parameter, which is r. Okay, the only parameter that remains is r. And we want to know how the dynamics, how the time evolution of the generation by generation depends on r. Okay, clearly we will not be interested in the case r smaller than 1, because the population is decreasing. Okay? We already showed this for Malthus. If r is smaller than 1, by Malthus law, they have a certain population, then r next population is smaller than this one, and then therefore this term here is also smaller and smaller than 1, and getting close to 0 has no importance, will go to 0. Okay? So we want r, which means this population is viable. Okay? It's not a population where the death rate is bigger than the birth rate and it gets extinct after some generation. We want cases where the population is viable. Okay? Okay, now, so coming back to this here, I just wanted to show how this can get ugly in a very few steps. So this one is okay. This is just using the equation for t equal to 0. T equal to 0, then you have n of 1 is equal to this. Nice. So next step is calculating n at time 2. We apply again the same formula, and then you say n1. I know n1. I can just calculate it, and I go there and I plug it in. Okay. So now you see this Malthus law, which was a linear equation, okay, was very simple. Okay. But now you have the nonlinear equation. You will have terms up to order n0 to the 4th. Okay, because here you have a square, and when this guy multiplies with this guy and this guy, will be n0 to the 4th, and this is just, we gave only 2 steps. Okay, if you go further, you get larger and larger expressions, which just it's not conceptually difficult in the sense that it's just using the same equation all the time. Okay, it's very automatic, okay? But you get enormous expressions, okay? So what do you do when you get this kind of thing? It's step by step, well defined, but it becomes too large, and we will not be able to solve the equation saying that for arbitrary time t, I know the expression in terms of n0, as we had with Malthus. We don't have this in this case. So we can do it step by step and calculate things. So then you say, well, I know how to do this. I just write down the program code for the computer, and he will do it. He doesn't care if it's ugly. Yes. So that's it. But before going for that, and we will do this, and we will calculate the dynamics with everything we have, all the beauty and of this kind of thing. But before this, we will go for qualitative analysis. We always like qualitative analysis, okay? So, therefore, let me go back to my first thing. So let me.
Okay.
Yeah.
I'm kind of confused. Okay. When this proportion, like the n t, tends to 1, so this is 0 because it's 1 minus 1.
Yes.
So
okay. When you are
what's the meaning of n t plus 1 is equal to 0?
If
n
yeah.
tend
when
no
n
the other one. This.
Here.
So n t tends to 1, okay? Because it.
Yes, I mean what you mean. No, it's not 10 to 1. When okay.
This is 0.
When nt is close to
to 1.
To 1, this goes to 0.
Yes.
And the population next time step has the same value as the population which was here. I mean, the population was 1, and next step 1 again because it's 0. Okay? So you get a constant.
So this measure the add time, the add number of individuals during generations.
No, you are not adding the population size. It's only.
But the population size is not 0. It's the add number is 0.
The added number?
Yeah, like if you add the variation.
Hmm?
Yeah, the additional quantity. Like I
Yeah,
have.
the additional quantity of individuals.
So this number is the additional, not the number of the population, like the total.
Yeah, I mean you are accumulating. Yeah, say.
She's pointing out.
Yeah, okay, it's yeah, right. Yeah, and it's the size of the population at time.
But this is not the size.
She.
It's the variation.
Like if it goes 0, it will go all 0, so the population size will remain the same.
Yeah.
What? Sorry.
If here
Okay.
we had a 0, so we be all zeros, and this population size will stay the same because it's calculating the variation, not the population size itself, right?
Let us come to the qualitative analysis, and you will see,
Okay.
because this is not as simple as we think. So maybe I a little bit I use some liberty, some freedom of expression of calling this K equal to be the carrying capacity, because, well, we are induced to do this because we have the carrying capacity from the logistic equation. So this K, yeah, it was good that you asked me, because I'm given, sometimes I'm jumping some steps. Okay, this K is as mysterious as the carrying capacity. As I say, the carrying capacity is always not well defined and so on. It is a measure of it's a population, reference population, okay, which okay, this will be the carrying capacity. But actually, I will show you that for many cases, the population will tend not to K for infinite time. It will tend to something else, which will be the carrying effectively the carrying capacity. And we will see that there are many problems with this model because it has this kind of thing. It's not accumulation. If n gets to 1 here, actually to 1, then it goes extinct in the next generation, which is weird. Okay? Weird. And therefore, we will have to modify this equation in the next part. Once we study this equation, we will modify the equation to avoid this kind of bizarre effects. Okay? This is because actually the carrying capacity will be smaller than K. And this will be a highly overshooting. And so much that it will oscillate in such a way that it goes to 0. That will be the final thing. Okay? So, okay. So, sorry if I called it carrying capacity by induction, but it is. I didn't show you that for large time, that the population goes to K. I didn't show this, and we will study this right now. So we will do it in computer, but before doing the computer, we'll do a qualitative analysis, and then we'll see it, with the computer it will be easier to see that there are some bizarre things. And some of them we could keep, but there are some of them that we can't keep. Okay? So, and then we have to modify the model because the model has problems. Okay? So, I will make the plot of n. Okay, I have n of t here. I have n t 1. It's a parabola, like the logistic equation. Okay, n t plus 1 it's a parabola with value 0 at n equal to crossing 0 at n equal to 0, n equal to 1. So the 0 here. Let me make it bigger. Now it's okay. I'm not good with drawing. Okay, so imagine this is a parabola. Okay, and I will draw a line which is nt plus 1 equal to nt. Okay, so just a diagonal here. Okay, I would say that it's something like that. Okay, my line has difficulties with getting exactly to 0, but that's a line, okay, which will cross somewhere here. Okay, and now we will start, say, at a certain point here, which I call n0. Okay, at the time 0, I have n0. Okay, so I go here. And I get n1 here. Okay? Now I want to put the n1 here and get n2. But n1, I can just use this diagonal here, okay? And reflect it here, so I get n1. Okay? Everybody follows the step. This is an auxiliary line, which is the identity. So I want to get this guy here, so I just reflect it here because this is the line nt plus 1 equal to nt. Okay? So, okay, and then I can get n2. Okay? I reflect it, I get n2 here, and I do the same thing. I get n3 here. Okay? I reflect it, and I get n3 here, and I reflect it. It will approach this point. Okay? That's the carrying capacity. Okay? And in this bizarre thing, the carrying capacity depends on R. Because R, with different values of R, I will have different parabolas. Different initial increase of the parabola. Okay? So this is called cobwebbing. And the two is cobwebbing with two B's. And now we can do it again, but you know, let's do it in a simple way. Here's my thing. Here's my line. I start at n0, but I now can do just this part here. You see, I started with n0, put n1 here, and then I reflect, I get n1 here, and then I get n2, and I reflect. But I could just do this like I start here, therefore I do this. Yeah? It's automatic. So I start with this point. Okay? So that will give me n1 here, and then I just do this. And that's it. This dynamics gives you a constant population. And now, let us ask the question, this constant population, which I can call the carrying capacity because it's where it goes, but it depends on R, so because all of these equations at the end only depend on R, not on K. Okay? So, if I have different values of R, I have parabolas that start, say, if R increases, it will have more steeper parabolas, okay? So let's look for something.
Sorry, I think that I missed something. This line, what is the purpose of it? I think that
nt plus 1 equal to nt.
Okay.
It's the diagonal.
Okay, okay.
Here it's not a diagonal because I'm not a good drawer.
Yes, okay, okay.
Okay? And if I use the real thing, I would have messed my thing. So that
Okay.
imagine, okay, that this is the diagonal.
Okay.
Okay?
Uh-huh.
I'm very bad with drawing these things. It's always when I teach this, it's the same problem. I can't. So now I want, yeah.
More question. So the line will cross exactly the peak of the parabola? Or
No. It crosses here. At
okay,
certain point.
okay. At some point, okay.
Okay?
Uh-huh.
But now, this depends on R. I mean, if you look at the equation, I wrote. If I start near the 0, okay, and I want to see the group population growth, okay, then near 0, 1 minus something which is very small is negligible, okay? And what is R? R will be the inclination of the parabola at the point 0, okay? So if R increases, I have a more steeper parabola, which will go through 1, because that's sacred. But you can have something which will grows steeper. Okay? So
Sorry, I think I don't understand. The carrying capacity is the point where the lines cross, right?
Yeah.
But why after that the population still get growing and
no,
just
stop growing. Stop growing here. Okay?
But
if you get on this point exactly, you are on the line nt plus 1 equal to nt. That's the definition of this line. Therefore, you stops there.
But the parabola keeps.
But the parabola is you never get to this point.
Okay.
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 We will see situations where you get.
Oh.
Okay, but
maybe we can see that point as a fixed point, right?
Yeah.
So because the population is just stuck, because you say that the next
Yeah.
generation is equal to
yeah, this is a
another.
fixed point. Okay, if I say this, this is what is a fixed population. For the next generation, it's the same. Okay, some generation, you stay there. Okay, so if you could substitute this here and write nt equal to r nt 1 minus nt and solve the second order. Not even one. You can cancel one. You get the expression of nt.
But there are examples in the nature that we pass this line, like.
Yeah, I mean, you could have started it there. Okay.
Oh.
Yeah, you could have started. I started here. Okay.
Yeah.
And then, well, it will be the same thing. You go here, okay? And then you get here, okay? And this guy you will no. Here, okay? Then you reflect, you get here, and then you reflect again, you get here, and you get back to this point. It's an attractor.
Okay.
Okay?
Thank you.
You can start here. Yeah. You don't need to start near the zero. It's just convenience. Yeah. Mike.
I forgot the name of the line that you're.
It's a diagonal.
Okay.
It's just y equal to x. And
So how I will know, I don't know, the angle that I have to put this line to calculate?
Okay, that's the problem of my drawing. This line is always this. It's
an equilibrium.
It's not an. Yeah. I mean, it's nt plus 1 equal to nt. Okay. So, but I just draw it very badly, so it doesn't look like that, but it is. Okay.
Okay, thank you.
It's just okay. You can if you put cobwebbing in Google, cobwebbing. Well, you will get at first of spiders, but cobwebbing, discrete time cobwebbing. There are those Java applets and so on. You can see this and so on, or you could write a program. But okay, so now. I want, let us go for the same thing here, but this parabola is steeper, okay? And we will cross the parabola, the line after the peak, okay? So this is just changing r, okay? R determines how steep you should start. Okay, we'll go from 0 to 1, but yeah, many times you can go like this, like this, like this, like this. Okay, and this is the value of r, okay, which will determine this. And now we do the same cobwebbing. Okay, are you okay with the cobwebbing at this point? Okay, yeah, you can say no, I'm not okay. I can explain again. Okay, I start with n0 here, then I get here. Okay, and I get here, and I get here. Oh, I'm approaching the thing. Okay, then I get here, okay? And then I get here, but then I get here. And then I get back here, and then I get here, here. So I'm circling around this point. Okay? So to see this more clearly, I will draw a super steep parabola. Okay? And do the cobwebbing. Okay? So this is the, we would say, the putative carrying capacity. Okay? But here, this means that you overshoot. Okay? Because they are now over it. And once you overshoot, you get here, and then you get here, and then you get here, and you get here, and here, and here. Therefore, you are jumping between this and this, this and this and this and this and this, and you don't get here. Oscillations, which were absent in the continuous time. Yeah, I mean, so first, discrete time dynamics is different from continuous time dynamics in this sense. Okay, you have oscillations. We can think that the reason behind this mathematically is that the dynamics at time t is not determined by the population at time t, but at the time t plus minus 1. Okay, so they have a time delay, and the equations with time delay have oscillations. Okay? This is not a fixed point. So, okay, you get here first. This guy here, you don't get to it. Okay, unless you start very here, maybe you will spiral out. Okay, so you get here, and then you get here. Okay, then you get back here, here. So you go from here, you go there, here, and then you get here to here. Okay, you are oscillating. You don't have a fixed. I mean, there is a fixed point here, and it's actually unstable. This fixed, yes, and what you get is oscillations around. So the population now has size, say, 0.5, and then 1.5, because overshooting. No, 0.5 to 0.6, then it gets back to 0.5, 0.6, 0.7, oscillate between two values. So this is called a bifurcation mathematically. Okay? And you now have what we call a cycle. And you will say you have a cycle of period 2, because after 2 iterations, you got back to where you started. I started with a certain value, I go to some different value, but I get back to the value you started. So this is a cycle of size 2. Okay?
Okay. And the 4 fixed points in the cycle would be unstable, or 2 are unstable? In the cycle, we have 4 fixed points, right?
No, you have 2. You don't have. You have 1 fixed point here.
Okay.
That's the only fixed point.
Always, oh, okay.
So you could say, I don't want to start here. I want to start somewhere near this guy here. Okay. So let's say I start at a certain point here. Okay. Then I go. And I do the cobwebbing, okay? Here, 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 here. You get out and you approach the cycle again. So this is called a cycle, and it's actually what in mathematics is called also a limit cycle, because it's limit of the dynamics, okay? So, nice. So this is oscillating between two values, okay? Now,
Professor, this happens when we have the relationship with a predator and prey.
This is not the same thing.
This is not the same thing?
No. Oscillations of predator-prey dynamics are different. Oscillations comes from the discrete nature of the generations. Now, I'm not claiming that this is the best model, and if this is actually something that you will see. We will discuss this at the end of of our mathematical part, we will discuss if this is reasonable. Okay? I mean, there is 6 populations that oscillate. And not all populations go to constant carrying capacities and so on, but oscillations exist in nature. Okay? Now, it's the nature of these populations, of these oscillations. Where do they come from? That's the big question about population dynamics, is where the oscillations, regular or irregular, come from. Okay? So this is saying that discrete nature of the non-overlapping generations can make you see this kind of oscillation. Okay.
So in this last example, first you started there, very near the 0, and then you started over there. So the 2 points that you oscillate between does not depend on n0.
Does not depend on n0. It's a global attractor.
Okay.
Okay. They depend on the particular R. I mean, yep. Okay. The R will give you different parabolas. Therefore, you get different values. Okay. So let me do a final calculation before we go for the numerics, which is let me put it here. And let me see my drawing abilities. I will put a parabola which is very steep and does this. Okay? 0, 1, and I do the cobwebbing. Okay? So in this case, I could have the following. Okay? Once I get here, okay? So I do this, and it takes 4 iterations to get back to the thing. Okay? It's not just a simple cycle like that. Okay? You will oscillate between 4. Okay? So if you use the name cycle, and I say this is a cycle of period 2, then this first one would be a cycle of period 1 by extension, and this is a cycle of period 4, and then you can ask yourself if there are cycles of period 8. So this is a period doubling bifurcation. That's the name of this kind of thing. The period doubles when you go for higher and higher values of R. Okay? So, very nice. But let's do this numerically now. Okay? It is not difficult. And actually, with what you have already learned from Sarah and Adriana, you will look at this very easily. And I won't explain the codes. Because I don't have time, but the real reason is I'm very bad at coding, okay? So I just take programs from other people and so on and adapt things. And I'm not a good guy with coding, but it will work. Okay? But it's a very simple program. Okay, so this is I'm using Anaconda, as you saw yesterday with Adriana. This is Python, welcome to Python, and so on. Yeah, this is a Jupyter notebook. You are now more or less acquainted to this, okay? It's not anymore a mystery. So, and I have a code. It's the same thing as Adriana. I get NumPy and matplotlib, all the things I need, and I define the logistic function. So the logistic function, which I will call logistic equation power, which will depend on R and X. The entries are R and X. R is the parameter, X will be the variable. Okay, so X is my N. Okay, I didn't want to change all the things to N, but X is N. Okay, and R is R. So the logistic the definition of this function is R times X 1 minus X, which is exactly the expression we have above there when if the n is the x, okay? So I can plot this. So let me do this from the shift. Where is this? Shift enter. Okay, logistic, and this. So you plot it. Okay, that's what we had. Okay, but I don't want to do the cobwebbing now. I just want to iterate and see what happens. Okay, so there's a code that I have no intention to explain to you, but it will just do what I think. It will do the iterations. I calculate from n0 to n1, from n1 to n2, and so on up. And the entries are only, there's this variable seed, which is the initial value, n0. Okay? Then there's the other entry, this is r, and then you have the number of iterations. I mean, I have to tell how long I want to iterate. I don't want to go into infinity. I have to stop iterations up after a certain point. And also, there is a variable which is used for plotting, which is skip the first and skip iterations, because we don't want to look at the transients, okay? So the transients are not live. So I don't want to look all of this. I want to go to the attractors directly, okay? So you don't need to plot the transient, okay? Sometimes you can do it, sometimes not, but if you go for more complicated things, it spoils I mean, it makes things. Now, so let us go. Okay.
How did you define the
what?
The skip. How do you find the skip?
So n skip is a value, and it appears here in the thing that if the iteration is smaller than n skip, okay, it's larger, and then you do the appending and so on. You are creating something that you will plot, but you won't plot the first iterations, because the first iterations are the transients.
The value of n skip you arbitrarily
it's
set.
Arbitrary, and we would start with 0. Okay?
Okay.
But at a certain point, when we get to more complex things, the 0 will be very not good. Okay? So okay. So going over this thing of the coding. So the seed is the initial population. I can use whatever I want. I put 0.8, but whatever you want, you can put. Okay. So R is 1.5, and I will iterate 100 times only. Okay. So I go there, and what happened? Whoa. Okay. It's too big here. I mean, okay, I have to. Okay, so this is time going from 0 to 100 time steps, and what you see is the result of the iteration. It is one by one, but it seems continuous because it's very close. 1, 2, 3. It seems continuous. This is one by one, and it got for a fixed point. Okay. So R, it's small r, you get to fixed point very quickly. I mean, I could have plotted only 20 if I wanted. After 20 iterations, I would be at a fixed point. Okay? So now we will play the game of changing the value of R. Now it's 2.9. Okay? And we look at what will happen. This is the situation where you get to the fixed point, but you get oscillating around. You oscillate, but the oscillation has smaller and smaller amplitude and goes to the fixed point, which to the carrying capacity. But it's overshoots, then it goes back below the carrying capacity, and it overshoots again, but it overshoots less. And then you get back, and so you oscillate. So in physics, you would say the damped oscillation, but it's not physics. Okay, very good. So instead of doing the control shift, it's easier to
Professor.
Run the. So now,
Professor, but it really reaches the carrying capacity, or just are oscillating in the scale that we can't see, like in this plot?
Oh wow! Yeah, and, yeah. It will be approaching asymptotically in the same sense that you approach asymptotically
the carrying capacity
in the continuous time, and then or with smaller r, you get only asymptotically to the carrying capacity always. In this case, you get asymptotically oscillating.
Okay.
Smaller and smaller oscillation. So now I go to a higher value, 3.1, and I will run it this way. It's a little bit easy. Where is the... So with 3.1, okay, with the rate equal to 3.1, and plotting the first 100 oscillate, you get exactly something which oscillates between two values. Okay, so this is the cycle that I showed you graphically here. And the computer says, okay, that exists. I mean, you were right. There are situations where you have this cycle. Okay. So now what we want to do is to increase. So we have what we call a bifurcation, a period doubling, where the period was 1, and now the period is 2. Okay. Now we want to go further, and we go to 3.44. You will see that you already see that it gets weird. We get by smaller and smaller steps in R in order to see what we want. Okay, so you run this, and what happened? Still oscillates, but it's a larger oscillation. Okay, so it's not only for one value of R that you get the oscillation between two values. There are several values of R where you get an oscillation between two. And that means there were several values of R where you got directly to the fixed point and you stayed there. And now there's a range of values where you get to the oscillation. Okay? It's not for one specific value of R. Okay? So now, and okay, I plot the solution here. I mean the values, and you can see that this is actually, if I do this this way, did it get exactly? So I will. What happened? Okay. With 100 iterations, you are not really actually at the point. I wanted to show you. I mean, I will use only some parts here. Okay, 0. More, less. Okay, so I got it. You see, because at the third digit, you still have some, because I didn't go to infinity, I did just 100. Okay, so you have 0.84, then before you had 44, then you have 84, and so on. So you keep going and repeating.
Professor, I'm understanding what's happening mathematically, but could you give me an example what would happen on a population, a real population? What's happening?
So, okay. In this case, you would have, the prediction, let's say, is that the population has a certain value in a certain generation, then you have maybe a larger generation, and then you get back to the previous value of the generation, and then you get up, and you get down, and you're up and down. That's what this says. Now, this we did this here by a mathematical reasoning that we could get the effects of the density dependence by just using a logistic. But okay, let me speed up a little bit. Maybe we will overshoot the time by 5 or 10 minutes, but it will be fun, okay? So, okay, so forget this. And so 3.5, we run it, and okay, now you see it's oscillating, but what is happening? You are, say, here, then you got here, then you get a different value, then you get still a different value, but then you get back. It's a period 4, okay? And if I do it correctly, here I should see a period 4. Okay, I see a period 4. You see, you are here, 1 step, 2 steps, 3 steps, 4 steps, you are back. Okay? Period 4 oscillation. Yep. So, okay. Then you do it, okay, that's, we had already done this. 3.5. Why did I repeat this? Huh? Idiot. Now I will skip the first 1,000 steps because it takes long time to get to the cycles. Okay, so I will plot 100, but it's the last 100 from there 1,000 before. Okay, and okay, so I go to 3.55, and here you are still in a cycle of. Oh no, you are in a cycle of size 8. Okay, you are here, 1 step, 2 steps, 3 steps, 4 steps, 5 steps, 6 steps, 7 steps, 8 steps. Got to period 8. And then obviously you will get for some value or some period 16 and so on, yeah. But the point is, when you look at this, you see I have done a very small step from 3.5 to 3.55. Okay, and I will have to proceed by going always with smaller steps. Okay, so then you do this, you get this oscillation. It's still a regular oscillation. I will try to see how many there are. This is still a period 8, so there is a region of values of R where you have period 8, and then you go for 3.565, very small increase. Okay, you run it again, you get some oscillations, and we will look at the period. Let me see. And it's a period 1, 2, 3, 4. Okay, that's still 8. Still 8. I don't know why I plot this. Okay, still 8. We want to go further, so I go to 3.69. Okay? I'm now going very slowly. Okay, I run it, and let me see what I get. I got a period 16, probably 1. I mean, this is either 16 or 32, okay? It's 32, okay? I didn't get the 16. I went too quickly. But you see that now you have this bifurcation from 1 to 2, and then 2 to 4, and then from 4 to 8, and from 8 to 16, and 16 to 32. But the increase of R gets smaller and smaller. So the values of R, when you have the bifurcations, are getting smaller and smaller. So you could ask, they could maybe go to infinity, accumulating at a certain point without R going to infinity. Yeah, this would be nice, yes? So you do this, and well, then you pick up in textbook which is the good value to choose for the parameter. That's a, okay? And you run it, and you get, okay, I plotted instead. I run again, because so there's still no oscillation, but this is probably high period oscillation. Okay, it's not even even exactly an oscillation. Okay. Yeah, you have a certain period here, okay? It seems to be, okay, this is misleading because I don't think it has reached the, okay, that's, so you have in the interval of 100, you have only 2 oscillations. This is probably 32 or 64, okay? So, okay. Small and smaller steps. Then you expect that at a certain point you will get to something where you cannot see anymore. So okay, yeah, you got back to the cycle of value, I think 2. 1, 2, 3, 4, actually, and but this is an exception. Because we were having doubling of the period, okay? And now, let me see.
Professor, can I ask a question?
Yes,
it's me. When you had the Malthus model, the continuous and the discrete, they have the same behavior, very simple. But when you had the
don't have the same
logistic model, the continuous
this is the problem of this model. I mean, this model has the beauty. I mean, the glory and the misery of the model are the same. So, no, okay, just let me discuss this in a moment. Okay. Yeah? Okay. So I go on with repeated values, and I still have some irregularities. Oh no, this is not good. Okay, I skipped something. Okay, here. Okay, you are getting higher and higher oscillations. Okay, it's in principle this is regular. Okay, I mean regular oscillations, but you will be accumulating to very high period, and you will go to period infinity at a certain point of R. There's a certain point of R where the period is infinity, therefore there is no period. I mean, period infinity means it never repeats itself. Okay? So this is called chaos. That's a technical, people talk about chaos in many different ways. This is chaos. So this is, you will have a population that assumes a lot of values and that keeps on jumping and between different values, and that does not return to any period. It doesn't go to any carrying capacity. It doesn't have any defined period. It is irregular oscillations. Okay, it's difficult to find exactly the point because you have the roundings of the precision of computer. You have the idea that this is a very precise a range of values where you get this thing. And then actually what happens, and so I will do it just verbally, you can have a region of parameters for R where you have this chaotic thing, and then you get back to regular ones. The regular ones are period 3. And then it starts again, period 6, period 12, period 24, okay? And goes to another accumulation point where you get again chaos, again irregular things, and so on. Then you get, I think, you can start with 5 and so on, okay? So this is, if you want to see this, you draw a bifurcation diagram, which is the best seen here. Yeah, this is the value of R, and these are the asymptotic values. For after many iterations, if you get to a period 2, you will have 2 values. 1, okay, so this is the first. This is the first. This is a period 2. This is period 4, and then you go on and doubling and doubling. Okay, so this is a bifurcation diagram. Okay, so now, okay. What we want is to discuss if this is reasonable. So the first problem you have will be the following. I will use a very large R, 4.1. Iterate 100 times, and I won't skip anything. Happened something. What happened here? So you got out of the range, but if you look here at the values, you were doing fine for some time, and oops, you get to negative population, which is monster, okay? And once you get to negative population, you got to minus infinity. This has to be wrong, okay? This is not consistent. So there's a problem with this guy, okay? And what's the problem is that actually you could continue this if you get to this point, if you get over 1. Once you get over 1, then you get here, and you get some negative values. And therefore, this is not consistent. Problem. So, it's fun. It has chaos. It's had period doubling. But this logistic equation is not consistent biologically because it gives you negative values. How would you be the plot of something that is consistent? Principle. Now, it would be something that grows, gets on, but doesn't cross the 0. And this will be always positive populations. You can never get here. Okay, this is called the Ricker model. And I have even wrote down the expression, for instance. Exponential. Okay, so instead of having the linear relationship, this is for small r. For small r, you can put this as 1 plus. Okay? So this is this plot, and obviously we will have all the chaos and all the period doubling. It's very similar to this one, except for the tail. And when you have the tail here, you don't get to negative values, and it's consistent and will be okay. Yeah.
Professor, there is some value of R for which the logistic model can be biologically sound.
So, okay, R between 1 and 4. And yeah, okay, but now this has the chaos and all the things. You could say, okay, but isn't there anything that just looks like the continuous time case? Isn't there a discrete time evolution, the dynamics, which is just tends to fix a point, just goes to carrying capacity. I don't want all these oscillations. There are many things that don't have this. So there is, this is the Beaverton-Holt model, which is just something like that. Something like that will give you, if I draw the thing here, will give you this always for any value. Okay, and this is the carrying capacity, and this is the discrete analog of the logistic equations in continuous time. It's called the Beaverton-Holt equation, and it is n plus is some r time n of t over 1 plus n of t. That's Beaverton-Holt. Okay, so good. And okay, this is a sign that I should stop the. Okay, what a mess. Huh? Okay. Okay, save the books. So sorry. And, okay, I have to save the phone also. Yeah. Okay, put it in the box. So, just to finish the discussion, so there's something which analogous to the logistic growth and in the normal sense. But, well, you could also say, okay, but all of this, I mean, could there be in nature something like that? Yeah, because this is a very simple model with very complicated dynamics. And that's the title of the paper, which is a founding paper of this area by Robert May. Very simple models with very complicated dynamics, which would be something expressing an idea that there are mechanisms that are pretty simple, but which could generate a lot of different, very complicated dynamics with oscillations and even chaos. Okay, so you'd ask
Professor,
yeah.
In this case of Beaverton holes, we have stability.
Yeah, that's exactly the analogous of the logistic equation continuous time. It grows and gets to a fixed point.
And in this case, the variation of error is very small.
For any, this is good for any value of error. This is fine for anything. If I change R, okay, you will be changing this line. This means that the intersection will change, but it will always go in this way. There's no way, because there is no way of getting down here. So, okay, if you don't overshoot, never overshoot. It's impossible to overshoot because it cannot go down. It's always increasing. Okay.
So, if yeah, you can find a model, but if you want a model that has the behavior of the logistic differential equation, isn't the first one that you would think of like the discretization of the logistic equation? Because when you solve a differential equation in the computer, let's say the logistic differential equation, it's always a difference equation, right? The computer cannot represent the continuum.
But there are small time sets.
Is this the one, or
no? This is not the discretization. It's just a mimic.
Yeah.
Okay.
Because otherwise you can say
there's no big point of having this one if I can stay with the logistic. Okay. With the usual logistic continuous time. That's true. People don't use this a lot, but it's just an example that you can engineer a function that mimics what happens in continuous time. It's just this. But the last point that I wanted to discuss is, okay, now you say, okay, that's okay, fine. But you found complicated dynamics. You have chaos. You have non-periodic oscillations. Hey.
Just a question before. The axes there are t. Am I right or not? Just to confirm it.
Oh, and t?
Because we have different axes, I think. T plus 1. But in the Beaverton Hall model, we have t as an x.
No.
Yes? No?
No. This function, n t plus 1, plot this function, it gives you something like that.
Okay.
This function, when n is small,
okay,
it's just you can neglect 1 plus n can be neglected. Okay. It gives you just Malthus.
Okay, cool.
And if n is large, then nt plus 1 is approximately nt because it's large.
Okay.
Then this cancels and that goes to an asymptotic value, which is r.
Okay. Could we test some cobwebbing there just to see if it?
Yeah, I mean here.
Okay. Okay.
Yeah.
Okay.
Anywhere you start, here will give you the fixed point.
Okay.
So there is the question. It's the question of is there chaos in nature, which is of this kind? In nature, not in biological populations. Do biological populations oscillate chaotically or not? Okay? Difficult, because this is oscillations without any period. Chaos means no period, never gets back. And then you have your data, but your data have errors. and you cannot exactly know. But yeah, you could do it in the lab. Okay? So, there are populations, in the nature, there's a population that oscillates. People do very precise observations and so on. And there's a discussion that would be the following. Okay, what would be the value of R which represents real biological things? Is this value such that it is in the chaotic region, or is it just some regular oscillations and fixed points? And there was a study over 22 kind of not meta-analysis, but meta-study, 22 oscillating populations that could be chaotic, and it turned out that the people inferred are by some fitting, and it turned out that 20 of them were just regular oscillations, and 2 of them were chaotic. Where chaotic means the inferred value of this guy here is in the chaotic region. But these were things in the lab where you manipulate the things. So the classical things is with flies. Okay? So you have the flies, then you have next generation, the eggs and the larvae, but you can manipulate the birth rate and the death rate. Okay? Because you can just go there and get out some of the eggs or put some from, okay? So it is a manipulated birth rates and death rates, okay? And so if you manipulate this artificially in the lab, your flies will solve the logistic equation, okay? You will make it do the chaos and et cetera, but this is a manipulated thing. And the other one that they found was something with tomatoes. There was also some agriculture problem. It's also something that you engineer the things. So it seems, this is not a, this is a question that's not decided, but it seems that this kind of thing are biological artifacts. Okay? At least the chaos region, not the oscillations region, it's okay. You see periodic patterns in nature. You have periods in nature. So this is not out of... the question is, okay, but with this I get to chaos, okay? So what are the actual values of R in nature? So will I be in a chaotic region or not? And the answer is normally not, unless you have some intervention which forces the system to go to a chaotic solution, but this is, you are manipulating the birth and death rates in the lab. Then it's not anymore ecology, it's just playing around a little bit, okay? It's playing around with the birth and death rates, and well, so that's nice, but it's an example. But in general, chaos is not present in, if you go for most of the time, for the populations that you see out there, okay? And so this is a kind of negative result at the end of the class, yes? Yeah, I showed you how interesting it would be, but we could do all of this, and we could work with discrete time models, and there are reasons to work with discrete time models because non-overlapping generations exist, but we ended up with chaos. And obviously, when the people found this, I think in the 80s, there was a whole hype, chaos, with all of kind of things. In physics, there's a lot of people that do chaos, and there is chaos. But here in biology, people searching for chaos, and so this was also a path of research that actually was sterile. It was not the best thing. It's a little bit like Joshua said about Lotka Volterra in the first class. So this took people to look for lots of situations trying to find chaos just because chaos is fun. And this is actually not the best way. I don't say that these equations should not be studied. They should be studied because they have non-chaotic regions and can be interesting. Okay? But usually, I mean, just saying, oh, I found chaos in biology. No, come on. You found in the model, and you usually don't see it in the nature. So this is an example of something which was researched pretty much. And actually, when you go for most of the ecology books, textbooks, or even mathematical textbooks, it is sometimes given as a chapter of some interest, but usually sometimes you don't even see it in the more biological things, because it has not been really relevant for the ecological theories and so on. Okay, so that's a good point to as something as an advice for people. Something people do the math, the mathematicians and physicists, and then they found something very nice and weird and so on. Calm down and look if this is relevant. Otherwise, you are just playing with numbers. Okay? Good. Thank you, and sorry for the delay. And well, there will be books again. Okay? There is the book on